Welcome to lecture 5. Today is the last lecture that will be sort of introducing the most basic pieces, the most basic Lego blocks of deep learning. After that, we can basically put them together in all kinds of new ways, but you'll basically have covered all the important stuff. It will be kind of the hardest lecture of the quarter, and I encourage you to read the lecture notes that we'll upload by the end of this week and really go through it, come to office hours. Today is sort of the heavy stuff, and then after that it will get a lot easier. We'll start introducing the real models you may actually use in practice. We'll introduce tools to you like TensorFlow that will allow you to make use of these basic blocks very easily, and we're good. The mic's not on? Yeah. Okay, all right. For the people online, today will be hard. So first we'll go over a little bit of organizational stuff. Then I'll give you some project tips, because now is also a good time to start thinking at least about the problems that you want to work on. And then we'll introduce the multi-layer neural network and how to train it and all the nitty-gritty details of the derivatives. And then we'll be good to go for the rest of this quarter. All right, so some organizational announcements. We'll actually introduce a 1% extra credit for Piazza participation. So if you see a question from somebody else and you know how to answer it, and you do that a couple of times, we'll give you some extra credit. Also, there was a little bit of confusion in problem set 1 around the dimensionality of some of the vectors. And so generally, the best way to go about doing this is first you figure out the math, you understand exactly what the dimensionality should be, and then after that you can basically check them with either breakpoints if you use something like PyDef and Eclipse, or with simple print statements. And so, for instance, if you have here the softmax cost and gradient function and you want to test something, you can always just say print v hat of the predicted dot shape, for instance, or the output vectors dot shape, and then you can check and make sure they make sense given the equations that you have. And then last night we also introduced the student survey, so I would love to get your feedback so we can improve the class. It will sort of moving forward change for sure, because we can go higher and higher level, start to put these basic Lego blocks together. So we'll stop after, I think this class, basically we'll stop going through all the indices of various derivatives, but it'll still be great to have your feedback and know if we're going too slow or too fast, and or just the right speed. All right, are there any questions? The organization, the problem set? All right. So the class project, it's really one of the most important and lasting results of the class. It's 40% of your whole grade. In order to facilitate making it easier for you to create a cool class project, we'll actually make problem set 3 a little easier, so you have more time on the class project. We'll also introduce in problem set 2 new this year TensorFlow. It comes with a bit of baggage, and you need to there's a bit of a steep learning curve in the beginning, but once you mastered it, you can put these models that we're talking about in the class together with a few lines of Python code, and then everything else will be automated. So this lecture will go through what's actually happening in the back end of a library like TensorFlow, but then you don't actually have to do it anymore because it can be fully automated. So it's a really powerful tool. Problem set 2 is really the corner piece of the class, and for you the first step towards your class project. It's likely that a lot of you may reuse parts of problem set 2 also for your final class project. So start early on both problem set 2 when it comes out, I think next week, but also on the project. So if you're done with problem set 1 already, you may start thinking about the kinds of tasks that you want to tackle. So in terms of project types, there are roughly 4 that we often see. The first one is just applying an existing neural network architecture or model to some kind of new task that is relevant to maybe your research or just generally something that you find interesting. The second type, and we'll go over what a little bit more in detail what this entails. The second one is to just implement a complex neural architecture that goes far beyond the kinds of things we covered in the class. So for instance, there will be attention or memory mechanisms, neural Turing machines, dynamic memory networks, more complex architectures. And that is definitely more advanced than the first type of project. The third one is even more advanced, which is to come up with your own new neural network architecture. I think you will soon have all the basic Lego blocks to start putting them together in new and creative ways, but it's also much harder because it kind of entails number 1 and 2. So in some sense, you put work on top of number 1 and number 2, so you can really only tackle that if you start early and you really want to get into the zone and work in this field a lot more. And then number 4 is quite different, but I know there are a couple of double E and stats majors and PhDs, and so that is definitely an option also, which is basically the theory of deep learning, looking at optimization, looking at saddle point problems, looking at better optimization techniques or things like batch normalization and other kinds of complex and novel ideas on how to better optimize these non-convex functions that come out in deep learning. Yeah.
So for 3 and 4, you obviously have the very big problem of they're unlikely to work on a first pass. What happens in that case?
That's correct.
Deadline comes, and do you just report why it didn't work and what you will try next time?
Yeah, so I discourage most of you from 3 and 4 for exactly this reason. This is really, if you're a PhD student and you really want to get into this field, then you might want to do this, but they're very high risk, especially if you come up with a new neural network architecture and you don't do it well, as in you don't start with project number 1, project number 2, and you implement something to show that you did some work, and you just try to start playing around with models and none of them work, and you don't come to office hour and I can't give you any feedback. And in the end, it basically is unclear whether your code was entirely buggy, whether you ran anything, because none of your numbers actually work and none of your code produces any reasonable results. So that will not go very well. Likewise, if you say, I tried to prove something really hard and I just happen to not get anywhere, it's tough to grade that and give a good grade. So this is especially number 3 and 4. I would only encourage you if you're really in the zone, you're at least a master's who wants to go to a PhD or already a PhD, and you want to deep dive into this, no pun intended. Especially in those, I would encourage you to come to office hours very frequently, especially to my office hours. Yeah.
Your project will be related to natural language processing?
Yes, so most of these number 1, 2, and 3 ideally are. So, and I'll walk you through what doing just number 1 would entail right now. So basically, you start with defining a task that you want to solve. So let's take, for instance, summarization. It's a little more interesting, less common than classification, which we'll cover it a lot. We covered a lot in class. So that's step 1. Think of something that you're actually excited about and that you would like to have a deep neural network do automatically for you. Then step 2 is define your data set. And we give you extra credit also if you're able to define your data set and run a first experiment before the milestone deadline, because we know it's often very time intensive. It's not very hard, and so it doesn't get you that much of the credit for the class because it's not really related to deep learning so far, right? Defining a task in a data set, you can do that and not implement anything that we learned in class. But if you understand everything you learned in class and then you get stuck on this, you also can get a great grade. So start early to define your task, come to office hours, and I'm happy to chat with most any kinds of tasks that you can think of. There's probably a data set that somebody has already tried to tackle this task with. So there are 2 options for defining your data set. The first one is you can just take an existing academic data set. So for instance, for summarization, there's a document understanding conference, and they already have nice baselines. There are papers published about those academic data sets, so when you implement your model, you immediately know whether you're onto something, you basically are pushing the state of the art, or whether you're far behind simple baselines and you may have a bug, or you may not understand the problem very well, and so on. So that is, I think, the best thing for most students. Now, the second option for defining a data set is much harder because if you define your own, you create your own, you write a crawler for Reddit. One, it takes a lot of time. Two, also has nothing to do with deep learning, so it's hard to give a great grade for writing a crawler for Reddit data or Twitter data or any other kind of data that is online. So I would only encourage you to do this if you're a graduate student, you already have a data set maybe from your research, or you're working with a professor already and you have some interesting psychology data set or finance data set or natural language processing, ideally, kind of data set. And so in our case, for instance, if you wanted to build a summarization algorithm, you might say, well, I'll download Wikipedia and I'll try to summarize the Wikipedia page, the entire page, from just the intro paragraph, or the other way around. From the entire page, I basically produce the summarization that is just the introduction paragraph. And then I write a little crawler, Wikipedia has a nice data set that you can just download it in its entirety, but it's also very big, so you need to have a big machine, and that's a problem that you'll run into a lot as you define your own data set. You'll need more machine power. And then you might pre-process your data, and you've tried to, in the end, get a proper input, output data set. Your creativity is really, there's no bounds here. We have some people who asked already about music data sets, for instance, generating lyrics or other kinds of things, or you can really come up with any kind of sequence data set that you want. In fact, I'll also be very lenient when it comes to definition of language. So if you have the language of music or the language of genes, as long as you use the kinds of models that we cover here in the class, I'll be okay with that. But if you don't have an obvious NLP task and data set, do check with me to make sure it makes sense in the office hour. It'll be again today for 2 hours, starting at 4:30. All right, now you have your data set, you have your task. The next step will be to define your metric. That is also an easy pitfall. If you have, for instance, a data set that's very skewed, let's say you have a simple binary classification problem, but in your whole data set, 95% of all your data points are in one class. And now your metric is accuracy, which is just total correct divided by total number of data points. Then you would get 95% accuracy by just giving the majority class every time. So that will also not be great, because that shows me that you weren't close to your data and you didn't carefully analyze the distributions of your labels and what your data set is like, and you chose the very wrong metric. And if you ever submit a paper like that and you're unlucky enough that the paper gets accepted, it would kind of ruin your reputation in the eyes of a lot of other researchers if you made that kind of mistake. So it's very important to choose the right metric for your task. So in this case, does anybody know what you would use as a metric if you had a very skewed data set distribution?
You could use your F1 score.
That's right. That's right. You would use F1 scores, which I think we'll define later on in this class too, instead of accuracy. So for summarization, what is very commonly used is Rouge or Rogue. It's a recall-oriented understudy for gisting evaluation. It's interesting abbreviation, and which basically defines n-gram overlap. So imagine your algorithm generates a summary of some larger text, and you have humans that generated summaries of larger texts. Now you basically look at how many n-grams overlap between your automatically generated summary and the human summary, or multiple summaries. So that seems like a reasonable metric to capture how well your summarization algorithm works. Now, step 4 is to properly split your data set. It's also a very common mistake in any machine learning project, and it's very important to not make it, which is you want to take, let's say you have 10,000 training data, training examples, you want to split them into a train, development, and test split. And sometimes the def is also called def set or development split. And basically, a reasonable split would be 80% of your examples will be used for training, 10% will be used for development, testing, and then on the remaining 10%, you only evaluate ideally 1 week before the final project is due. Maybe you're okay with testing it once a week. And you really shouldn't test more and more often on your final held out test split. Now, even in splitting, there are some mistakes that you can make. So for instance, if you have a lot of things that are very similar, but then they change over time, and you want to understand the test set ideally gives you an idea of how accurate your algorithm would be in the real world, where you just took another couple of random Reddit messages or tweets and you now evaluate your algorithm. So if your test data looks very similar or it has duplicates, for instance, in your training data, you overestimate how accurate you would be. So you want to make sure there are no duplicates in your development and test data to your training data. And if you had a time series, for instance, the best thing would be to actually take out the last month of your data and have that be the test data. So you train on 10 consecutive months, then you have the next month be your development split, and then the next month after that your test split. That way the algorithm would give you your results will be very indicative of what the performance would be in real life. So there's some mistakes that you can make here, and what I encourage you in many cases is to be close to your data. Do look at what your data set looks like, look at some examples. If you have the report, show some examples. You're doing sentiment analysis, show some of the interesting sentences that you have. You do summarization, show us in the project report, and look at yourself, like, is the algorithm, would this even be possible to predict this from your inputs? And show us as graders also how hard your task is by just looking at real examples. Are there any questions around splitting your data set and defining your metric? Yeah?
Around what size of the data set should we strive to look for?
That's a good question. What is size is good? It kind of highly depends, largely because your output space can be very different. So far we've only looked at classification. If you only have binary classification, then maybe having, starting at 1,000 examples per class starts to be reasonable if the task is not super hard. Not all training data is equal. Ideally, you'll have a distribution that is somewhat indicative of what your final testing distribution is like too. So if you have, for instance, you have 10,000 training examples, but again, 99% are in one class, and only the last percent is in the other class. That's not that helpful. In fact, then you could have another 1 million examples of the majority class, and it's still not going to help you that much to find that really rare class. So, and then there are other tasks like summarization that are much harder, or machine translation, which is probably one of the hardest tasks in NLP and requires the largest amounts of training data too. And there you start to going into the gigabytes, basically, like a lot of training data, because machine translation is such a complex output space, right? It's the entirety of the target language that you're trying to translate into. So, but roughly once you have 10,000 examples of something and the distribution of your labels is not totally skewed, you're usually in good shape. Cool. All right. I think we have 4 more steps or so. So the step number 5 is to establish a baseline. And that's especially important if you have a new data set that nobody else has worked on yet. But it can also be helpful, even if it's a publicly available data set, to just make sure your training split is correct and you can replicate roughly baselines from the literature. So these can be very simple models. You can download open source packages like scikit-learn. We don't really care that much about how you get to those baselines. In many cases, like logistic regression for unigrams and bigrams, if you have a classification problem, for instance, are fine. But basically, establishing a baseline helps you to make sure you understand you have properly split your data set, you have properly defined your metric, You're using now properly your development test set and not your final test set. You don't just look at your training accuracy, which will often be very high, especially in deep learning, but also in standard methods. You can already know, you can analyze your errors, you can visualize what is the baseline actually getting wrong, so that it might give you some intuition of how you want to design your deep learning model to improve over the mistakes that the baseline makes. And then you may get into the somewhat lucky stage if you're just an industry and you're just trying to solve a problem to make some customers happy. But in our case, it wouldn't be that ideal. If you just implement your baseline, you collected your own amazing new training data set and some interesting task, and now you basically run the baseline and it just solves it. It just gets 100% or 99% test accuracy. At that point, you probably chose a task that was a little too easy. And if the task is really interesting, then let's chat during office hour, and maybe it's okay. But in most cases, you either made a mistake, you have a lot of duplicates in your test set that were already seen in training time, or the task is just way too easy, and probably a very simple method would suffice, and then it doesn't really make that much sense to implement a fancy deep learning model. That's likely going to take a lot more time, because you can't really improve that much over your baseline. Then we finally get to the actual stuff of the class, and this is why you want to start early on these projects, because to do really well, you want to have enough time at the end to actually spend on steps 6, 7, and 8. So now that you have established your baseline, you have your task, you can basically implement some existing neural network model, likely one, for instance, that we used and introduced in the class in one of the problem sets. Then you can, again, compute your metric on your training and your development splits. You can analyze the outputs and the errors, and that's kind of the minimum that you should do for the project. It's really the bare minimum, though, because really what this means is you can just run problem set 2, the code of problem set 2 on some new data set, and just rerunning problem set 2 code on some existing data set. It's not that exciting, but that's sort of the minimum bar to pass if you take the class like pass-fail or something. Now, once you've run this, again, be very close to your training data. Oh, I have a question? No. You're always close to your data set. Visualize it. You can, for instance, visualize the distribution of the labels that you have. You can visualize just some examples that you see. You can look at a confusion matrix, for instance. And especially, you want to look at the errors that your model is making, because that might give you some intuition of what the model might be missing, and then you can improve it in step 8. And very importantly also, you want to analyze how the different hyperparameters affect your performance. So these are all sort of standard things that we will check off as we look through your final project report. So I encourage you to go through these steps in your project. So for instance, we already know a couple of hyperparameters like word vector size. The hyperparameter could also be size of your training data. And what you'll often observe is that as you increase your training data set size, the accuracy also will improve. And sometimes it will improve more than all the things that we could do on the model side. Any questions on how you can be close to your data or establishing your baseline? Cool. So now we come to the most exciting part of the project, which is to try out different model variants that you may have and that you may have thought of based on the errors that you've seen in your simpler neural network models. And you can already start, but really starting in the next, by the end of next week, you'll have a lot more options all of a sudden on what you can try and all the different, how to put together the different Lego blocks. So for instance, we've already seen the word vector averaging model, also sometimes called the neural bag of words model. And we've looked at the fixed window neural model. But then starting in the next lecture, we'll actually get to recurrent neural networks, and then in the weeks following, we'll have recursive and convolutional neural nets. And I think recurrent neural networks are really the best default model for a lot of NLP tasks. And so that's why we're focused on that a lot during, in problem set 2. In TensorFlow, we'll have a special lecture on just recurrent neural nets, and then advanced recurrent neural nets, and one on TensorFlow for recurrent neural nets. So hopefully you'll be all very familiar in the end with those, but also understand the trade-offs between these different models. Cool. All right, now the advanced, just one slide on the advanced option of trying to create a new model. The tricky bit with that is that really the ideal way to do this is as essentially step 9, after you've done all the previous steps. Because it doesn't make sense to implement some new fancy model if you don't know that on that task, a simple baseline or simple neural network would already solve the task. So you first really want to gain intuition of why all the existing models are flawed for the kind of data set that you have. And there is a bit of a shortcut here, or cheat in some ways, which is you look at the literature, and we'll show you a couple of papers here that essentially do this for you. So if you look at, for instance, sentiment classification, I have a bunch of papers. We post a couple of them on the syllabus too, and you'll see, oh, people have already tried all these different baseline models, so you don't have to really restart there from scratch. But we'll never penalize you if you do. So I still encourage you to look carefully at those baselines. If you want to do this, ideally you will talk to other researchers. Don't try to do it all in a vacuum by yourself. Definitely come to my office hours. I usually the last half hour, so it gets pretty empty. So there's plenty of time every week. You want to implement your new models and then very quickly try to iterate over ideas. So machine translation, for instance, as much as it's a really great task, it's probably not the right task for this class, because generally experiments in machine translation, even if you have a very sophisticated implementation on a GPU, it will take around a week to get one number and run one experiment. So if your data set is very large, the larger it is, the less quickly you can iterate on your model. So you want to set up some efficient experimental framework. We'll help you starting next week in setting up TensorFlow. We actually got the Myth cluster to have TensorFlow installed now, so we're happy about that. We're trying to get it on the Rai cluster too, which has GPUs. And we'll help you also set up AWS, so Amazon's Web Services. So you can, in theory, run on 100 GPUs, but each GPU machine costs, I think, 65 cents an hour. So don't go too crazy if you want to do that. Of course, if you work with a company or you're an SCBD student, you can do whatever you want, but we can't really reimburse all the AWS costs. So though I do think every Stanford student actually gets $75 for free of AWS credit. So if you haven't used that yet, you can definitely make use of that extra resource and essentially launch a couple of extra machines. And I think those are all, it's a little bit of extra work for the TAs, so thanks to the TAs for figuring that out. But I think it's a very useful task nowadays in the world to be able to understand how you set up essentially a new computing cluster for yourself, right? And if you don't go too crazy, you don't have very large machines, and you don't let them run for many weeks, it's a pretty cost-effective method to just get a couple of GPU machines, run some experiments in parallel. All right, so always start with the simpler models and then go up in your complexity, in the complexity of your model. So for instance, for summarization, we may start with a very simple average word vectors in a paragraph, and then just do a very greedy search of trying to find like what word to predict next, for instance, something very simple. Then we might implement a language model where we try to predict the next word, or an autoencoder, which both of these models will introduce later. But basically, you can start with something very simple in almost all the tasks, including sentiment analysis. Just average all the word vectors and try to predict something with a deep neural network. And then this one would, for instance, be a fun sort of stretch goal or an extra bonus point question if you want to have one of the top sort of projects of the class, and you could try to actually generate the whole summary instead of just kind of greedily selecting words for the summary. And that would be very hard. So you need a lot of training data for it and so on, but people are able to generate sentences with deep learning models, and we'll cover how to do that starting in the next lecture. Cool. Are there any questions around general project steps? And
for the baseline, you give the example of just regression. Should we tune? Like, should we optimize the hyperparameters, or is that no longer a baseline?
Baselines should always ideally be tuned, and they should be given the same TLC or attention as your own model. There's some people who often say that if you read papers in the literature, you should always implement the second best model, because that probably didn't get as much tuning, but it still works almost as well or close to the best model of the paper that the paper usually introduces. So it's definitely good to at least try like unigrams and bigrams and a little bit of the regularization, for instance, and a simple sort of bigram logistic regression model. Definitely that is very encouraged. Great question.
So we talked a lot about tasks such as named entity recognition, summarization, sentiment analysis. Are there any other interesting tasks that might not be as popular but might just as well be interesting?
Absolutely. So there are tons of interesting problems out there. I often talk about these just for sort of educational purposes. They're easy to understand, and then we can focus on the underlying models, because then the underlying models are general and you can apply it to any other task. So here are a couple of other, well, including those, but also some other tasks. So there's named entity recognition, which we just talked about, and summarization. There's simple question answering. This is actually a really fun data set, and it's now also a challenge that people are running, where you basically try to predict simple facts. So who was the president after George Washington or something like that, and just you basically try to predict that out of a large set of possible entities. It's a very fun task, and one that hasn't been worked on as much, but Mohit and his collaborators have developed lots of different baselines for it, and so you can really see if you can do something interesting there. Image to text mapping or generation is a really fun task. If you've taken 231N and you already know how to take a convolutional neural network and get a vector representation of features for an image, then you can also train a model to try to map images and sentences into the same vector space. Again, the simplest model, for instance, would be you just take your word vectors, you average them, and you use the max margin objective that we'll cover in today's class, and you try to have them be close to each other, or have a large inner product of the sentence that describes an image versus sentences that don't describe an image. That's a really fun task. I think one of the coolest projects last year was actually people who had a real life camera feed. You could point it at stuff and it would just output what it sees in natural text. That was a pretty cool project. But it was also they even got an exception to have 3 people on the project because it was a pretty ambitious project. And I think the 3 of them were all PhD students, so no worries if you don't have a live demo like that.
What do you mean by image to text mapping? So you take the image and it maps it into the same word embeddings that we saw a couple lectures ago?
That's right. That's right. So you can co-train 2 models, 2 deep learning models, and don't worry yet, we'll cover all these kinds of models that you would use for this in the next couple of lectures. You can also just take the model and then train a recurrent model to predict the description. Entity level sentiment is a really fun twist on general sentiment. So the difference between general sentiment is you just say this sentence is overall positive or negative or neutral. But entity level is a little more interesting. You might have sentences, for instance, such as, I thought the iPhone was better than the Android. And now it doesn't really make sense to say that sentence was overall positive, because it was positive for one phone but negative for the other phone, right? Or you might say, the acting was a little silly, but I love the story so much that the movie was overall pretty good. So now acting is negative and movie is positive. So that's kind of entity level, the task of entity level sentiment. There are unfortunately not as many great data sets for that task, but it's a really interesting task that a lot of people in the industry care about a lot, like going through Yelp reviews and extracting different aspects of a restaurant and then basically enabling you to search for the best atmosphere, maybe not the food as much because you don't want to eat that much anyway or something like that. And then most tasks on Kaggle, I think that question already came up in one of my office hours. Can you use Kaggle datasets? Absolutely. It's great to use Kaggle datasets. Kaggle is a machine learning competition website where basically companies or sometimes universities upload datasets, and there's a nice leaderboard, and you can see exactly how well your model does compared to hundreds of other groups that all try to tackle that task. And I don't know if there are any competitions that are going on right now that actually have a deadline that fits with the class, but of course if you win a Kaggle competition, you have a almost guaranteed pretty good grade because it's very hard. And usually they come with like a huge pile of cash too, so they're quite fun. And then I've been asked for sort of a default project, and one of those would be sentiment analysis. We've covered it a lot in class. And this is a data set that I had introduced during my PhD. Hundreds of researchers have since worked on it, and it's basically a very nice, clean data set. It has a train def test split already. It's harder to mess it up. So if you are kind of busy and you just want to get a passing grade and you don't want to think too much about some creative task in the world, this is a reasonable data set that has clean labels. It's going to be big enough to train deep learning models, and it's just a very simple thing. It's hard to do something really impressive on that data set just because hundreds of people have already worked on it and pushed the accuracy pretty high, and it's very unlikely you'll be able to even get to that accuracy by re-implementing a lot of the state-of-the-art methods, because even just replicating some of these top models is a lot of work. So it's not like the most exciting project, but it's it's a reasonable baseline project. Cool. All right. So that was all about the projects. Any more questions about projects? If you can't make my Monday office hour, just shoot me an email. We can try to figure out some other way. I really encourage you to come to office hours. Cool. All right. Now let's get to the hardest and most exciting bit. I think after this, a lot of deep learning will kind of lose its mystique or magic, and you just realize, wow, I just need to keep track of indices and know the chain rule really well. And then I understand all these crazy deep learning papers, and I could implement them from scratch myself. But it's not going to be easy, so let's get to it. All right, so let's take the basic idea of the window model, where we wanted to basically classify the center word here. And let's, for now, assume we just have a very simple binary classification problem where we want to say, is the center word a location or not? Now, towards the end of the last lecture, I introduced the single layer neural network model that basically just had a single linear layer followed by nonlinearity. And remember again, f could be a sigmoid function or tanh, any kind of squashing function. The simplest one that we've looked at in the class so far was the sigmoid function. And we now basically call A here our neural activations. And we can use that feature vector now instead of the original window, which was the concatenated word vectors here in X. So again, X is the definition here. For a single window, we usually just use it X to define the concatenated word vectors of that window. Multiply it by a matrix W. The number of rows of W is the number of hidden units that we have, and basically defines the dimensionality of our neural activations A here. So those can now be seen as our features. And now what we can simply do, instead of computing a softmax probability, is we can just compute an unnormalized score with another inner product here. So just basically summing up, having a weighted sum here of our features in A. So that's just a single number, and that's our score. And if that score is high or above 0, we'll say this is a location. If it's low, Below 0, we say it's not a location. So that's our straightforward model. Now let's visualize what this model would look like. Here, again, we concatenate all our words. Let's say, for instance, each word is 4 dimensions. Each bubble here basically represents a single number. Then we often write a layer like this. Sometimes you also see connections to all the different nodes, but that gets pretty tedious and messy looking once you have a realistic number. And even with such a small number, it gets very messy. So sometimes you just abbreviate all these connections with a single arrow. And then we have just a single score. And again, you might say this is a 3-layer neural network or a 1 hidden layer neural network. Now, one thing that will be very important is to always define what the dimensionalities are for all the different parameters that you have, your hidden layers that you have. And so we write this out very carefully here. For instance, x is a column vector, so 20 by 1 vector. If we have 8 hidden units, then w has to be an 8 by 20 matrix, and then u has to be an 8-dimensional vector again. Sometimes I like to write out the score function also as like one entire function, which will help you sometimes to think about the chain rule a little better. But we can also define intermediate terms, because that will enable you also to know exactly which parts of the chain rule to define properly. Yeah.
So in the second row of the picture, we have 8 circles. Do those represent z or f of z?
That's a good question. Usually they represent f of z. It's the final thing. And then, but we'll also, I think in one figure, I'll split it up so you can kind of see how the errors change as you go through the network. Okay, so the main intuition, just on a very high level, of why we might want to add this layer and not directly train the classifier on the word vectors themselves, is that we might want to have nonlinear interactions between the word vectors. So for instance, museums, if museums is the first vector here in this window, should it matter that in is in the second position? That's the kind of feature that you can learn once you add an extra layer in between. If you don't have an extra layer in between and you just classify directly, then basically just says, if I see this kind of word at this exact location, then it's either, indicative of a location or not. But if you want to actually have combinations of words that are captured in the window in specific locations, then you need to have a second layer. Cool. All right, so let's summarize the feed-forward computation of this first neural network and with this example here. So let's say we have, for instance, a window. We go again through the windows, just like when we train word vectors. We go through the windows and we say we have a correct score whenever the center word of that window is indeed a location. And we were going to want to maximize this score here. And now that's basically just giving the algorithm positive indications of these things should be high. But if you now optimize only scores to be high when they have a center word, then you only basically, there's nothing that would prevent the model from just making all the weights very, very large and giving high scores for everything. So you want to always counterbalance and teach the algorithm with negative examples as well. Now the question here is, how do you create negative examples? Well, that it's usually very easy, which is you just take a bunch of windows that don't have the center word as a location, and you'd have those as negative examples. Another option could be you corrupt the existing window and you just say replacing the center word with a random word. So for instance, museums in playing are amazing. So just some random word like a verb, and then you'd say that would be my corrupted window, and I want to lower the scores of that. So now to put those ideas together, for each window, we will have this main objective function. Basically, the idea will be to make the score of the true window S to be large, and the one of the corrupted window lower. Hence, if we minimize this, then S will get larger, and SC, the corrupted score, will get smaller. And now this idea here is a really powerful one. We'll see this kind of objective function a lot during this class. It's essentially a so-called max margin objective, where intuitively here, after you train for a while, your model might realize, like, I have moved to something that's always a location. And you don't need to teach the model again in the new window that to increase the score of that window, because it already knows how to do it after having seen a couple of examples. Now what this model, this objective function will essentially help you do is that if the score of this correct window is indeed already one higher than the score of the corrupted one, then you will just switch to 0 here. So intuitively, for instance, let's say you ran through this computation, your final score for this museums in Paris are amazing is 5. And you take some random other window, such as not all museums in Paris. Now plus is not a named entity location, and that scores only 0.5. Now you take 1 minus 5 plus 0.5, and that overall is smaller than 0, but your objective function basically takes the maximum of these two numbers. And the maximum here would then be 0, and hence you can ignore that window. So that's one really powerful advantage of having the max margin objective versus the softmax. The softmax does the same computation and the same training every time, even for examples where it's essentially done. It's already doing the right classification during SGD, during training. But here, after a while, you can stop doing backpropagation on examples where the model is already very certain about getting the right answer. So since this is still a continuous objective function, we can perform stochastic gradient descent just like we do with the softmax. Okay, intuitively, you can also think of the max margin to essentially try to define a better decision boundary. So if you have, for instance, two word vectors, cool. If you have two word vectors, and let's say you have a positive example here and a negative example here. Now there are lots of ways you can try to compute a decision boundary to distinguish one from the other. You could, for instance, say this is my simple linear decision boundary. Of course, that's not a very robust decision boundary, because if you now have just another example here that's also in that class, then that would already get misclassified. So intuitively, what you do when you have a max margin objective function and you have these kinds of examples is you try to maximize the distance between the two different points from your decision boundary. And you want to make sure that that is at least 1 until you stop caring about that example. All right. Okay, now there's no magic here. We'll basically just take derivatives now of this kind of function in order to optimize this neural network with the max margin objective function. Are there any questions so far? Okay, so that is just the objective for a single window. Now you could sum over several corrupted or other windows that aren't in this true class. So you could sum here over a couple of different random windows that aren't right. And of course, in the end, you're going to sum over all the training windows to compute your complete objective function. But in SGD, we're going to subsample always a small batch. All right, any questions? Okay, so now let's go into backpropagation. So this is basically our main function, and we only have to really look at scores and derivatives when the cost function for that window pair is actually larger than 0, right? Again, if it's this part is smaller than 0, you just jump to 0 and there's nothing to take derivatives off. Derivative with respect to all our parameters of 0 is just 0. So now we'll compute the derivatives of the score S and the score of the corrupted S with respect to all the involved variables that we have, which will be U, the final scoring layer, W, the weight matrix of our first hidden layer, W, the bias B, the bias term, and X, our word vectors in that window. Now, because S and SC are basically the same, I'm just going to go over S, and you just basically have negation in front of these two to differentiate the two. So let's start with the first derivative of S with respect to U, our final scoring layer. Well, that was quite easy. It's just a simple inner product. In this case, A is just a fixed constant because there's no parameter inside that we're trying to compute the derivative for. So the derivative of S with respect to U is just A. That's the simple one. Now let's look at the weight matrix W, which starts to get a little trickier. So let's write out very carefully what the terms are. So this is something that I sometimes do just to show you sort of what the terms are and how we can play around with them, and to make it very clear that while we might write A here, really A is defined in terms of f of z, and really z is defined as wx plus b. So it's very important to keep track of when you define variables that actually have other variables inside, or parameters that you're taking derivatives with respect to. Now let's look at a single weight in that entire weight matrix W. Let's look at the single weight Wij. Now you remember, for instance, for W23, that's basically in the second row, the third column. That's the element of W23. And we also remember that at every neuron basically comes from one row of our W matrix. So the first row of W defines the weights for the first neuron, and the second row of W defines the weights for the second neuron. And here we'll have, just for illustration purposes, a very, very simple neural network where we have just 3 input numbers and our bias term B2, and we just have 2 hidden neurons and the final score function S. And so when I write U2, for instance, the sub-index here is just the second element of the vector U. And W23, for instance, is the weight that defines how important the third input is for the second neuron, and how much we weight that element, for instance, of a word vector. Any questions so far? Cool. All right, so let's take the derivative with respect to Wij. So let's write out very carefully what that final score actually is and how we computed it. So each step here is very simple, but in the end, when you look at it sort of from afar and you just spaced out for 2 minutes, you're going to be like, oh my god, what just happened? So we have to look very carefully at each step, because each step is indeed very simple. So remember here again, we just have our chain rule. So if you have, for instance, some function y that's defined in terms of u, you just basically compute this product. So now let's look at our chain, the application of the chain function to this. So Wij of u transpose A. Well, u transpose A, we really don't care about u1 and a1, because we know that W23 doesn't even appear in any of these parts, right? The parameter W23 only appears when we look at A2, if we look at W23, for instance. So in the general case of Wij, we really only need to look at the ith element of the hidden vector. A. So let's look at the derivative, the partial of ui times ai with respect to wij. So, well, ui is just a constant in this case, so we can just pull that out. And then look at the derivative of ai with respect to wij. Now, ai was just defined in terms of zi's, so we can apply the chain rule here and basically write out what this means, which is the derivative of ai with respect to zi times the derivative of zi with respect to wij. And again, we know that zi was defined as just the ith row of w times x plus bi. We also know that ai was just basically equal to f of zi by definition, so we can plug that in here. And for now, since zi is just a single number, what we can simply do is just write f prime. Whatever f is, it will have some kind of derivative. The sigmoid has a derivative. I think you'll derive it in your problem set. It's very simple. And so we just write for now f prime and keep that general. And then we have the derivative of zi with respect to wij. And again, we just plug in the definition of zi, which is this simple inner product here of this row vector times this column vector with respect to wij. So let's copy that over. And now when we just write that out very carefully, this is basically just an inner product, so it's just a sum over the dimensionality of how many columns we have. So let's say we have k equals 1 to capital K columns. We just basically multiply these two numbers with one another. I have this weighted sum here. And now again, we know that from the first lecture when we looked at the word vectors, the derivative of the sum is just a sum of the derivatives. And really, wij only appears when k equals to j. All the other ones are constant as well when we look at the derivative of wij. I'll let that sink in for a second. Okay, so now that we basically, the derivative of this sum with respect to wij is just xj. Now here comes the first and important trick of backpropagation, which is we will define a delta, which sometimes is sort of called the local error signal, or just some people kind of confusingly call it error message, but really it's just the best terminology for this is the local error signal. And so we'll define delta I as just this simple product of ui times f prime of zi. And xj is just our element of the word vector here, and we'll call that our local input signal. And here's just one definition, for instance, for f prime if we use logistic function, often abbreviated with sigma. And we'll notice here that very conveniently, f prime is actually can be computed in terms of f of z. Why is that nice? Well, that means we don't have to compute a completely new function with the exponent during, when we take the derivatives. Because this kind of function is much easier and cheaper to evaluate than if we had to run another exponent to have another complex derivative. And in many cases, the kinds of nonlinearity functions f that we'll use will actually be computable. The derivatives of the functions f will be computable in terms of just f. Okay, so far I haven't really given you any reason of why we defined this term here with a new special variable called delta. But it'll become very apparent when we realize, well, instead of wanting to just compute a single weight, ideally we'll compute all the weights of all the different wij's. And so the question here is, what could we do if we wanted the combination of I equals 1 to 2, the two hidden neurons here, and j equals 1, 2, and 3 for our three inputs? what would be if, let's say, those two were, for instance, vectors, where we have delta I for I equals 1 and 2, and we have that as a single vector. How could we get the combination of all the partials? Outer product, that's exactly right. So the derivative of j with respect to w here, assuming j was larger than 0, will just be delta times x transpose. So if this is a column vector and this is a row vector that we transposed, then we'll basically get the nice outer product. So it's a 2 by 1 times 1 by 3 vector, and then we'll have exactly the right dimensionality of a 2 by 3 matrix. And so another terminology for delta is the responsibility, or again, error message, coming from each of the activations of these neurons. All right, so this was all the gory details of the first layer. We'll get into 2 more gory details, and after that we'll just kind of zoom out for the rest of the class. So now is your time to ask some questions. Did all the steps here make sense? Were there any questions around over these steps? Yeah.
Is there any intuition behind why it's called local error signal?
Yes, so basically the delta will kind of tell you how important was xi for the overall error that you make in your total objective function. So in our case, the score and the max margin objective function. So as you go further down the network, which we'll do in a bit, you'll notice that the deltas will get smaller and smaller often, because the changes will make less of a difference to the final error that you have, or the final objective function that you have. Yeah.
It looks like here, like x and e are column vectors, but in the homework they're row vectors. Is there a reason to prefer one or the other, or like separate dimensions?
It's kind of an implementation detail. So Python sometimes, like NumPy, has a certain default. So the important thing there is just to make sure you print out what they are, and you make sure that you do the right thing. So there's no reason. I think there are, well, I guess in programming languages there are certain ways that vectors are stored, and matrices are sometimes stored as like column first or row first, and so there can be slight inefficiencies if you have to transpose it manually every time. Or
Given that, can we change our implementation in homework to match the math here?
yes.
Even if there are inefficiencies?
You can always, as long as your math is right, you can always change the implementation and the transposes and all those things. Yeah. Yeah.
How did we go from partial S over partial W to partial J over partial W?
Partial. Oh, great question. So here we wrote S, but then here in the final thing I wrote J, and I just kind of mentioned it briefly, but I probably glanced over it too quickly. So here we basically note that you're actually right, it should be minus, because we have here minus in front of it. But basically, when you take the derivative and you assume j here for this window pair is larger than 0, then you kind of can ignore the max 0 part, and then you just look at 1 minus s plus sc, and then derivative of anything with respect of 1 with respect to any of the parameters, this just goes away, and then we can basically focus on just s. But you're right that derivative of j should actually be minus s. Great question. But it's because it's linear and it's right there at the top of the objective function. That's kind of how we jump from one to the other. Great. Okay, so now let's look at the bias terms. So here we just basically have similar steps. UI, AI again just defined as f prime or as f of zi. We'll apply the chain rule. We end up in a similar spot to where we ended up for the derivative partial of wij. And so, but now we're with respect to bi, we notice here, okay, bi is just basically 1 for this derivative, so we end up with just the delta term that we had defined before. Yeah?
You see that j is max of 0, 1 minus s plus sc. Here, SC is also a function of your W matrix and the U, right?
Oh yes, of course, you're totally right. So this is doubly wrong, and you're absolutely right. We really, I should have just written S here. So the overall thing, and I think we'll get to that actually in another slide, because really this is minus delta of xt plus delta c times xc. You're totally right. I'll fix that.
They're double the number of parameters, or are they?
No, they're the same. They're the same W.
Okay.
Yeah, because you don't at test time you wouldn't know which one to apply, so you always have to apply the same one. Very good. All right. Several of you are totally on top of it. All right. So now that was almost backpropagation, but it's not quite. We're not quite there yet. But really, what we've just done is take a bunch of derivatives and applied the chain rule. Now the remaining trick is that we can reuse the derivatives that we computed for higher layers for lower layers as well. And so in the simple one hidden layer neural network here, that will come up when we try to actually backpropagate the error that we have into our word vectors x. So let's do that in a second. And again, this reusing of derivatives, the simplest form here we've already seen here. To compute the derivatives of b, we didn't have to actually do any more computation, right? Because we've already computed delta to compute the derivatives for w. And so to compute the derivatives of b, we basically reuse the same delta, right? So no extra computation had to be done. And now it gets even better because we can compute or reuse all those deltas as we compute derivatives with respect to a single element of that. So let's take, for instance, the example here of the derivative with respect of s with respect to one of the elements of x. Now the main thing that we'll notice is, unlike before, where W2, for instance W23, only appeared in one of these neurons, x2 actually modifies both of these neurons, right? And so we'll have to sum the derivatives as we apply the chain rule. So let's look at the example of derivative of s with respect to xj. So basically here we sum over our two neurons and apply the chain rule to both. We'll define here our final default score with respect to AI and AI with respect to xj. Now we'll again just define what this is. This is again a simple inner product, so we can write that out very quickly as UI. And then we apply what the definition of AI really is. That was just again f of wi dot times x plus b. Now we'll apply the chain rule, we'll get f prime, and lo and behold, that's the same ui times f prime of zi that we've had before when we computed the derivative with respect to w. But now we have this other term here, because we still have x, and derivative of this inner product with respect to just one element of that inner product, again, is just that element of this row vector. All right, so now we basically have this sum here that is just multiplying two numbers. Now, if you're familiar with linear algebra, how could we rewrite this sum in terms of a vector multiplication or a vector matrix multiplication? Or maybe just for the simplest one, it's just a straightforward vector multiplication with a column or a row vector of w. Yeah? That's right, just the dot product. So basically here, the important part of the dot product though is that we're summing over I. So we have to take the column, the jth column of w, transpose it, because now it's a column vector, we want to make sure it's a row vector, so we define properly our inner product and it doesn't become accidentally an outer product or something, times, again, this exact delta that we've had, which is just our two-dimensional vector. So now the amazing thing is we were able to compute the derivatives with respect to x using that same delta that we used in the computation before. All we had to do was multiply it by this w. Now, this was just for one of the elements of our window x. what should we do to get the whole gradient with respect to x1, x2, and x3?
Just the full W transpose.
That's exactly right, the full W transpose. So basically, as we have multiple of these inner products for each separate element of xj, you can just combine all of those, and here I did it right thing, it's just for s, derivative of s with respect to x, it's just W transpose times delta. So we had a linear layer, just the x's are basically right there, and all you had to do to get to them is multiply with W transpose times the error message that we had before, or the error signal. And now this is a very important observation, and it's a sanity check as you do these derivatives yourself. The error message delta that arrives at the hidden layer, in this case the word vectors, has the exact same dimensionality as that hidden layer. If it doesn't, you couldn't really update it, right? In the end, you want to have, you know, your x in stochastic gradient descent, your x new equals your x old minus alpha, your step function, times this gradient, right? So they have to sum up. All right, now I do the almost right thing, except this s should be j. So this is the full final objective function when we put all of these together. So we had here the gradients for s and for sc. This is sort of the indicator function, so if this part is actually larger than 0, then this is our final gradient. So we always have to sum up for the full sum here in our max margin objective, the a's, for instance, plus ac for the derivative of j, this should be j here, sorry, with respect to u. So that's how we put it all together. All right, now let's get to the two-layer neural network. So very important to keep track of all your indices very carefully here. So let's define x as the first input layer, and just for notational convenience later, we'll define this as A1, the first activations of the first layer. Now Z2 will always be computed with the parameters of W1 times A1 plus B1, and A2 just defined as, again, element-wise application of the linear layer output Z2. And then we can repeat the same exact thing, but with C3, A3, and we'll compute our final score S with A3 instead of just A2. All right, now when we take the derivatives of W2, which is the output here, it's really the exact same thing as we did before, but instead of having X underneath it, you have A underneath it. But that's completely independent as we compute the derivatives with respect to W2, so we can really go over those pretty quickly, and we'll basically have the exact same output here, which is delta 3, very carefully now defining the delta messages also in terms of a superscript, which is the layer that they're coming into. And then, but basically the computation derivation here is exactly the same thing that we had before, but with A2 now instead of X. Now, again, we defined delta here. Delta here we'll define properly and very carefully as this Hadamard product. The Hadamard product is basically just the element-wise product between these two vectors. So this vector, each element gets multiplied by the element, the corresponding element of this vector. So this is our definition of delta 3. So now the last missing piece for understanding general backpropagation will be to take the derivative of S with respect to W1. And now if we wrote that all out, it would get pretty messy. I encourage you to do it at home, but it basically takes all the exact same tools that we just used and apply them very carefully, keeping track of all the indices. And the main thing that you'll have to compute is basically the error message or the error signal delta 2. And it's a similar derivation to what we did in the single layer model. But the main difference here is that you'll have to basically apply the chain rule twice, and you'll notice that you have to basically compute all these or derive all these different terms. One way that might help you is to gain some intuition is just to assume all these numbers here or all these parameters are actually just single scalars. That might help understand sort of how to apply the chain rule, and then you just kind of have to make sure you understand how to do it when they're all matrices. And intuitively, whenever instead of having a single number, you have multiple nodes at each layer, you basically have to sum over all those nodes. And so when you put these various things together, you end up with a delta error signal that looks like this. It's very similar to the one we just computed, but you have to have also applied the chain rule to the next layer down. And so it's going to be W2 transposed times delta 3, and then Hadamard product of all these elements. So this is a vector, and just multiply these element-wise. And so the final derivative will be, again, delta 2 times x transpose, the same kind of outer product that we've had before. And so in general, and these are sort of the two main equations, if you go through that extra step, and I encourage you all to do it, it'll be very useful for the midterm and all other kinds of places, and after that it has sunk in. You fully understand backpropagation. These two equations are the main equations of neural networks. Basically, how to compute your delta error messages, which will always, in standard neural networks, will be of this form. And then you update and compute gradients for all your matrices W here. And that will always be the outer product of these delta error signals times the activations of that layer. And in many cases, we add regularization to it as well. And so I think personally, I think probably half of you find this sort of very careful derivation intuitive, but I know that for some people it makes sense to look at and visualize this intuition a little differently. So here's one last way, really quickly before we end, of also thinking of how backpropagation works. So let's say we have this simple function here, or this two-layer neural network, and we've already computed our gradient with respect to W2, which was just the first delta message that came in here, times the activations of A2. And here we separate out the linear, the linear layer and the element-wise nonlinearities that we'll define here as sigma. So F, in this case, is defined as just a sigmoid function. Now, what we're going to do is we're going to reuse, as we propagate the error back through this network, we're going to reuse this delta 3 and pass it through W2 by essentially moving this error vector across this simple affine transformation, this linear layer, by just multiplying it with the transpose of that forward matrix W2. And notice how the derivatives, the dimensionalities here exactly line up, because this delta had to have the dimensionality of this layer, and so when you transpose W2, you get exactly that dimensionality. And now, as we propagate the error through the nonlinearity, which was element-wise, well, what happens and what we need to do is exactly do a pointwise or element-wise multiplication with this local gradient that we now have of this nonlinearity. So again, we move through the affine transformation, we just have W transposed. Now we move the error through the nonlinearity that is element-wise, so we have an element-wise product here with sigma prime, or in our case, in general, F prime. And that now defines delta 2 to go down to the next layer. And so then we can define, again, the gradient with respect to this matrix as, again, just the outer product of that error message times the activations that come from that layer. Cool. All right. You survived the hardest lecture of this class, and I think next time I'll just start the first 5 minutes with another intuition visualization of Backprop, but it'll just be chain rules again. So we'll just have one more visualization. Thank you.